In this last section, we saw for the dynamics for the motivating case study using eigenvector-eigenvalue analysis. We divide this section into two videos. In this video, we intuitively and graphically explore the dynamics of the populations of customers. We reason that at long times, the dynamics are essentially one-dimensional. In the next video, we pursue this insight to develop an analytic solution for the dynamics of the free and paid customer populations. First, we briefly review the model. We said that you are managing an internet data storage company that provides users access to their data online. It's as though they virtually plug into their memory sticks by logging onto your website. We said that you have XP customers paying for premium accounts, and you have XF freeloaders using an introductory account with limited data storage capacity. You wanted to know how the composition of your user base will change with time, so that your accounting staff could determine whether the revenues from the paying customers would be able to sustain the expenses incurred by providing both premium and free services. To be able to predict dynamic changes in your customer base, we enumerated processes that could contribute to the dynamics of your customer population. We supposed that a paying customer could recruit a friend to try out your service. For simplicity, we said that in any given month, a fraction rho of the paying customer population persuaded a new customer to sign up for free service. For example, if the fraction rho were 3/8, then 3 out of 8 of the paying customers initially present at the beginning of the month would succeed in each persuading one friend to join the free customer base by the beginning of the following month. We were hoping that customers who tried the free service would like it enough to sign up for premium access. We supposed that a fraction upsilon of the free customer base would upgrade each month. For example, if upsilon were 2/9, then 2 out of 9 non-paying customers present at the beginning of a given month would get excited about your service and join the paying customer base by the beginning of the following month. We were concerned that some paying customers might decide that they no longer needed premium service. We supposed that a fraction delta of the paying customer base would downgrade from paid to free accounts. If, for example, delta were 1/4, then 2 out of 8 customers paying at the beginning of a given month would have left the paid subscriber roles by the beginning of the following month. We supposed that even non-paying users might choose to cancel their accounts. We said that a fraction alpha of the non-paying customer base would cancel its accounts each month. If, for example, alpha were 2/9, then 2 out of 9 customers who were signed up for free accounts at the beginning of a month would have completely closed their accounts by the beginning of the following month. We noted that this table of events, or so-called reactions, could be written down as dynamics in discrete steps in time. The non-paying and paying populations XF and XP at time t plus delta t could differ from the values of XF and XP at time t, owing in part to recruitment, owing in part to upgrades, owing in part to downgrades, and owing in part to attrition, which we used to refer to the cancellation of free accounts. We've chosen the time step delta t to be a month because we've been tracking changes in the subscriber base from month to month. We want to express the dynamics of these populations of customers in a simple way. We recognize that the expression of the populations XF and XP at time t plus delta t as linear combinations of the populations XF and XP at time t can be formatted more legibly in matrix notation. The condition of the subscriber base at a given time t can be thought of as a vector x, with components XF of t and XP of t, meaning that vector x of t is a linear combination of some abstract basis vectors f and p. The matrix with elements 1 minus upsilon minus alpha, rho plus delta, upsilon, and 1 minus delta describes a step in time of 1 month. Repeated applications of the matrix represent repeated advances of time in steps of 1 month. For example, multiplying the initial vector components XF and XP evaluated at time t by m copies of the matrix produces the subscriber base at time t plus m additional months. Before we perform a lot of algebra to analyze repeated matrix multiplication, let's think about the dynamics of the system qualitatively. Let's say that we send out early invitations to get users to try our service for free. So we have N non-paying users at the beginning of the month that we officially launch. We can visualize the state of the subscriber base by plotting the paying customer population against the non-paying or free user population, with both XF and XP normalized by dividing by N, the inaugural number of non-paying users. We are using the components XF and XP, or to be more accurate, normalized versions of these components, to establish a coordinate grid for specifying the state of the subscriber base at different times. Initially, the state of the system corresponds to this pink arrow. No customers have yet signed up for paid service. We only have the non-paying customers who responded to our pre-launch invitations. Some non-paying customers will enjoy the free service enough to sign up for premium service. Transfer of subscribers from the non-paying to the paying population corresponds to diagonal motion toward the northwest. Some non-paying customers, unfortunately, will lose interest and cancel their accounts. Loss of non-paying customers corresponds to horizontal motion toward the west. The state of the system thus moves toward the northwest, a little more west than north, as we move into the next month. Now that a paying customer base has been at least temporarily established, satisfied paying customers can start to recruit their friends to try the free service. Increasing the number of non-paying users corresponds to horizontal motion toward the east on this grid. This motion toward the east can start to compensate for some of the motion toward the west, corresponding to the loss of non-paying customers who cancel their free accounts. As the non-paying customer base swells, it then increasingly feeds into the paying customer base. As we've said, movement from the non-paying to the paying customer base corresponds to motion toward the northwest. Again, as the paying population expands, it helps to recruit more free users, corresponding to motion toward the east. Together, this motion toward the northwest and motion toward the east can produce a net movement, for example, that eventually points toward the northeast. This movement can point noticeably toward the east if paying customers recruit new non-paying customers efficiently. A subscriber base composed purely of non-paying customers generates paying customers because some of the non-paying customers upgrade their accounts. A subscriber base composed purely of paying customers would generate non-paying customers in part because satisfied paying customers recruit friends to sign up for free service, and in part because less satisfied paying customers downgrade to unpaid accounts. Neither initially pure population would remain pure. At some intermediate composition consisting of both non-paying subscribers and paying subscribers, the time rate of contribution to the non-paying population from the paying population, in a sense, balances the contribution to the paying population from the non-paying population so that the subscriber base composition remains unchanged. This statement is a little crude because we neglected to mention the attrition of non-paying customers, but we've captured the basic intuition. Pure populations tend to generate their initially missing counterparts. A particular composition of a mixed population can sustain itself. Thus, with time, the composition of the overall subscriber base eventually becomes arbitrarily close to a constant proportion of non-paying and paying subscribers. This is why the purple arrows representing the state of the system at very late times point at basically the same angle. They indicate a basically constant proportion of XF versus XP. Now that we've intuited that long-time population dynamics will essentially trace out a line, which is to say be essentially one-dimensional, we pursue this insight in the next video to obtain an analytic solution for the dynamics of the customer base populations at all times.